Hi guys, we're back. This is the third video and the last video for lesson number 1 of unit number 3, which is concerned on loss of radicals, specifically in simplifying radicals using the loss of radicals. For the previous two videos, we applied the concept of the fractional exponents and the multiplication and division laws respectively. As for this last video, we are going to apply or we are going to use the power law of radicals in simplifying radicals better. Let me share to you some items here I already prepared for you as the practice exercise C. So again, this video or practice exercise C is concerned in using the power law in simplifying these different radicals here. Just by one look at the following radicals, we have indices which are different from what we had before. What we used as indices before were actually square root and cube root, the two basic forms of radicals. But here, for items number 1 to 5, we have 6, 4, and even 12 as indices. So here, we could actually use the power law to simplify the items better. Let us use number 1. For number 1, we have the sixth root of 4. Of course, 4 is not a perfect six number. Okay? Because if we talk about a perfect six number, it is the result when we multiply a number to itself 6 times. The first perfect six number is 1 because 1 is the product when we multiply 1 6 times. Like 1 times 1 times 1 times 1 times 1 times 1. The answer is 1. The next sixth number is actually 64 because that's a product when you multiply uh, 2 6 times to itself. Like 2 times 2, which is 4, times 2, 8, times 2, 16, times 2, 32, times 2, 64. As you have noticed, that's already very large, from 1 to 64. And this radican here, being 4, is not a perfect six number. However, we can still simplify this better because we all know that 4 is a perfect square number. As for the power law of radicals, we could actually present, say for example, the index as a product of two different numbers. We could actually represent it as a combination of two different radicals with the factors of the original index of the radical. Or you could actually interchange this if you would like n here and m here. It doesn't matter because multiplication is commutative. In short, 6 can be written as the product of 3 times 2. Okay? With this, we could actually rewrite this as the cube root of the square root of 4. Take note that in the radical symbol inside the radical symbol, we don't have here 2 because squared is already 2. You could actually rewrite this also as the square root of the cube root of 4 because again, multiplication is commutative. However, we cannot simplify this because 4 is not a perfect cube. In short, the correct way is to use this than the first second form. Okay? So we are going to use this first form because we can simplify 4 as a square root. So what we will have here as our final answer, we still have cube root and the square root of 4, which is 2. In short, the sixth root of 4 is just simply equal to the cube root of 2. And since 2 is not a perfect cube number, that is our final answer. So we are going to repeat the processes for numbers 2 to 5 using the power laws. Let me move them down. Okay. So for number 2, you have the given fourth root of 18. Okay. fourth root of 18. Now, 18 is not a perfect uh, fourth number, nor 18 is not a perfect square number. But we can actually rewrite this. But 18 has a factor which is a perfect square. In short, we could write this as square root of, or let us write it better. That's 2 times 2, and then you have here 18. So that is actually written as square root of 18. Anyway, you can just, even if you will commute that the factors 2 and 2, they're just the same. Okay. And by the way, in 4, do not use 1 times 4 because we don't have 1 to root. Okay. So 18 is a product of 9 times 2. So we could rewrite this as square root of the square root and of 9, sorry, 9 times 2. As for our final answer, this 9 here can be brought outside, but just simply out here. So that's square root of 3. And since 2 cannot be brought outside, we have here square root of 2. It looks a little bit complicated, okay? But actually, that's the final answer. You could rewrite fourth root of 18 as the cube root, or square root of 3, square root of 2. Because again, 2 cannot be moved outside. As for number 3 is the sixth root of 9x squared. Similar to number 1, we can rewrite this as 3 times 2, and then the radical symbol 9x squared. We can actually try to avoid what happened in number 2, because in number 2 it looks complicated. Again, the do not write it this way. It should be until here, because that is what the original function, the whole. Okay. But again, number 2 is a little bit complicated. So to avoid number 2, in number 2 we can avoid it. But for number 3, we can avoid it by using the proper index that can simplify 9x squared. 9 is a perfect square. X squared is a perfect square. In short, cube root is placed outside, so that we can simplify the 9x squared using the square root inside. If you're going to interchange them, again, 9 is not a perfect cube, x nor x squared. So the answer here is simply the cube root. The square root of 9 is 3. The square root of x squared is x. So the answer is cube root of 3x. Number 4. Number 4 covers the given, that's of sixth root of 27y cubed. So same as number 1 and number 3, sixth root can be written as cube root, 3 times 2, sorry, of 27y cubed. As for number 3, we use the cube root outside because we know that 9x squared is a perfect square. For number 4, 27 is a perfect cube. Y cube is a perfect cube. So instead of placing the cube root outside, we will commute it and let's use the square root outside and the cube root inside for 27 y cube. So that our answer here would be a square root of, the cube root of 27 is 3 times 3 times 3. That's 3. And y for y cube. Because 27 is a perfect cube of 3 and y cube is a perfect cube of y. In short, the answer is now square root of 3y. Take note of the difference for number 4 and number 3. Because in number 3, we are actually, we chose the cube root to be what is the outside, and the outside index, and the square root is the inside index. For number 4, we chose the square root as the outside index because the radicand here can be simplified with the cube root, cube root index inside. As for number 5, let me uh, transfer a little bit 5 here. Okay. In number 5, we could actually use different methods here. But let's write the given first. Okay? So it's very big na po. 12th root of 81. I will show you two different processes here. Number one, we can rewrite this as 6th root of square root because 12 can be rewritten as 6 times 2. So we chose 6 outside and we chose the 2 inside because it is way easier for us to square to get the principal square root of 81 than 6th root of 81. So we have here 6th root of the square root of 81 is 9. And then 9 is still a perfect square. So we could actually rewrite 6 here as the cube root of the square root of 9. Again, we chose the cube root outside than the square root because 9 can be simplified using the square root inside. And 3 times 2 is just 6. So the final answer here is the cube root of 3. This is one method in answering number 5. That is if you're not familiar with other perfect nth numbers. But if you already know that 81 is another perfect nth number aside from being the perfect square of 9, 81 is actually the perfect fourth of 3 because again this 81 is actually 3 to the power of 4. 3 times 3, 9 times 3, 27 times 3, 81. So if we know that 81 is a perfect fourth of 3, you could just actually take instead of the 4 steps here, you could use another situation here using only 2 steps. 12th root of 81 can be rewritten as the cube root and of the fourth root of 81. 3 times 4 is 12, so it's just the same. Because we now know that 81 is a perfect fourth of 3. So this is just basically cube root of the result of the fourth of 81, which is 3. See, we have the same answers. This is using the longer method because we are not sure if 81 has another form of a perfect nth number. But if you know that 81 is another perfect nth number, specifically perfect fourth, so you could actually use this shorter method. But either way is acceptable because this is shorter due to the understanding of other perfect nth number. This is longer due to the multiple application of the power law, but still, they still have the same answers. So again, the purpose of simplifying radicals is for us to operate them properly later on. So this is the last law of radical, the power law. Use this video as you dig deeper in understanding radicals or simplifying radicals. And again, use this video in the first two videos because as a review, use them as a review because in next lesson, the operations or radicals, we are going to use these concepts before we can operate such expressions. Thank you for watching and stay tuned for the next videos. Goodbye.